And as you know, my today's session is based upon the first topic of operations research. Operations research is a kind of subject matter which is consisting of various optimization techniques. Those optimization techniques are based upon situations. On the basis of situations, we actually use different types of optimization techniques to deal with. Okay, you know, the optimization is the general word for minimization and maximization. So when we say that let's optimize something, so we may mean to minimize it or to maximize it. Now the thing is that this optimization technique will be defined or will be different with respect to the situation which you are dealing with. The very first situation which is there in the syllabus is called linear programming problem. I don't know whether you have any idea about linear programming problem or not, because I can see in the syllabus the linear programming problem has started. The topics of this chapter, linear programming problem, has started from simplex method. Now, I'm asking you, do you have any idea about what linear programming problem is? Answer in yes or no. Anyone? Have you heard of linear programming problem earlier? Do you have any idea? Okay, you have idea. That's very good. And have you done the graphical solution? You heard it and you know it. There is a difference between these two. Hearing and knowing. Have you solved problems on that? No. Okay. So since linear programming, some people have done it in their course curriculum earlier, because in MCA different people come from different streams, different courses. So in some people from your class, they have done linear programming problem, and some people have not done it. It's quite obvious. But since this subject matter is there, and I'm supposed to start from simplex method. Simplex method comes very later. Simplex method comes when when you know what linear programming problem is and you know how to solve them by graphical method. Suddenly you cannot start from simplex method. But I shall not kill many time on that because it is not there. So just to give you a little bit of glimpse about what what linear programming is, let me share my screen and this PDF file with you, so that from this you will get to know what I'm talking about actually. So just hold on. It's opening. Wait. Can you see my screen? Right in the chat box. Can you see my screen? Yes. Okay. Thank you so much. Now you see, just a minute. Okay. First of all, in this particular, in the first page, I have actually mentioned the syllabus. Syllabus was the course curriculum which I have written over here consists of a little bit portion of your syllabus. I have not included many because I have because this particular syllabus has some sort of similarity with syllabus of, say, for example, what I mean to say, this in this subject, whatever I have written over here, you can see that I have marked one as linear programming, and then in two I have marked transportation problem, assignment problem, and lastly I have marked theory of games. Other topics which are there in the syllabus have not been mentioned over here, because these four topics, that linear programming problem and transportation problem and assignment problem and theory of games, they are connected to linear programming problem. Transportation problem is a special type of linear programming problem. Assignment problem is a special type of linear programming problem. Theory of games can be solved by linear programming problem methodologies. So I have only mentioned these four topics over here. Okay. Now, here I have mentioned what we actually mean by optimization. And as I have already told you that by optimization, we actually mean maximization and minimization. Now, these are some sort of prerequisites. I'll share this note with you. These are some sort of prerequisite for studying linear programming problem. And most of the students are very good in mathematics. Most of the students from MCA are very good in mathematics. So they will not be, it will not be harder for them to grasp the idea of linear programming problem. Okay, I think that most of you are fully acquainted with the topics A to H, which can be considered as prerequisite for studying linear programming problem. Okay. So first question which I'm dealing with is that when a variable is linear, and it is you can easily see that the answer is when if you have an equation and if you can see that all the variables involved in the equation have power 1, then such an equation is called linear equation. So for example, x plus y equals to 1 is a linear equation because both the variables x and y have power 1. But if you give me an equation like x square minus 2 equal to 0, that is not a linear equation because the power of x is more than 1. Okay, so in this particular chapter, course curriculum, we'll be dealing with only linear sort of equations, and rather, or more in more general sense, inequations. So that's why it's called linear problems. And from which situation these linear problems are actually derived, this can be understood by the following. I have mentioned several situations where linear programming problems, you can see that linear programming problems can be formed from them. Various sort of situations have been discussed over here. Okay, so I shall share this note with you. So for example, I can consider a sample problem like say for example, a small manufacturer employs 5 skilled men and 10 semi-skilled men for making a product in 2 qualities. Okay, a deluxe model and an ordinary model. These are the 2 products they are actually making. The production of deluxe model requires 2-hour work by a skilled man and 2-hour works by a semi-skilled man. The ordinary model requires 1-hour work by a skilled man and 3-hour works by a semi-skilled man. Okay, and according to worker union's rule, no man can work more than 8 hours per day. The profit of the deluxe model is ₹1,000 per unit, and that of the ordinary model is ₹800 per unit. Formulate the linear programming problem. And this particular situation can be dealt, you can say that this situation is often used in labor management. Okay, so it's a kind of labor management type of situation. So various situations which I have mentioned over here where linear programming problems can be considered. This note which I have prepared, and some images have been taken from the Google to give you a feel of in what sort of situation these linear programming problems are actually used. This following example, which you can see in front of your screen, is an example of transportation problem. Okay, so this is a transportation problem, and actually this is a special type of transportation problem which is called a transshipment problem. I shall share this note with you. Don't worry, you don't have to worry about that. Today I'm not going to start rigorous problems and rigorous mathematics. I'm just giving you a feel of what linear programming problem is. And the way by which I'll be taking your class is not by presenting notes. Today I'm presenting notes in this first session, but actually I shall be doing some sort of board work when it is required. And obviously in operation research class, board work is often required. So, and this particular problem, as you can see, is a very good problem. It has been taken from a situation, a flight management situation in airports all over the world. This type of situation is actually dealt with. And I shall be discussing this beautiful problem with you in the specified time when the time comes. And it is a topic, this particular situation is a topic of assignment problem. Assignment problem, you know, is also a kind of linear programming problem. And lastly, a sample problem of game theory has been shown to you. Okay, so these problems which I have taken into consideration, these are all taken to give you a feel of what sort of problem, what sort of thing the linear programming problem is. Now I'm going to share a new note with you, and you just wait for that. The note which I'm going to share with you right now is where I shall be discussing, just a minute. Let me open the note where I'll show you how to formulate a linear programming problem. Okay. Formulation of linear programming problem is not there in the syllabus. They have started directly from simplex method. So to make a sort of continuity over here in teaching you the subject matter, I am considering this formulation part from a different note which I prepared in the last semester for MBA courses. They also had operations research in their syllabus. So I consider this note for them, formulation, and I shall redesign this particular note. I will change some sort of headings over there, and I'll share this note with you also. So today I'm going to discuss very briefly how to formulate a linear programming problem and what are the different parts of linear programming problem. Okay, so let's start. Now you see, let us consider this sample problem. If you have pen and paper in front of you, we can copy this problem. The problem says that the company sells two different products, capital A and capital B. The two products are produced in a common production process and are sold in two different markets. The production process has total capacity of 45,000 man-hours. It takes 5 hours to produce a unit of capital A and 3 hours to produce a unit of capital B. The product has been surveyed, and company officials feel that the maximum number of units of capital A that can be sold is 7,000 and that of capital B is 10,000. If the profit is rupees 600 per unit for the product A and rupees 400 per unit for the product B, how many units of each product should be sold to maximize the profit? Formulate the linear programming problem. Formulate the problem as linear programming model. You can skip writing this particular question in the paper also, because I'll be sharing this note with you after the class. So you can get it from there. You just listen to me what I'm saying to you. And if you have any doubt, any question, you can write in the chat box. So this is the question, and we have been asked to formulate the problem. Now, not only formulate the problem, a question has been asked in the problem, how many units of each product? Now, whenever this question is asked, how many units, that means you're going to find something. Okay, what that something is, that something has to be defined. That something here actually means the units of each product, capital A and capital B, the units of capital A present and units of capital B present, which should be taken into consideration to optimize the situation. Now, here, specifically the maximization type of problem has been taken into consideration, and the variable which you are supposed to maximize is the profit variable, profit. So you are going to maximize the profit. How to formulate this type of situation? Because once you cannot solve a particular problem until it is formulated. So here I'm going to talk about how to formulate the above problem. Step number one is that you have to identify the variables involved here and how many types of variables are present. Now, since in the question, it is mentioned that how many units of each product should be sold, let us consider that small x units of capital A and small y units of capital B be sold to maximize the profit. According to the question, we're supposed to find how many of small x's are there and how many of small y's are there. Okay, so first of all, you have to consider the variables X and Y for the different, different types of and quantities involved in the problem. These variables X and Y, they are actually a special type of variables. I shall tell you their, but they have a special name associated with them, and I'm going to tell you after the formulation what sort of variable they are. Though the people who already know what linear programming problem is, they know what these variables are known, or what are the names of these variables. Now, once you identify the variables, once you assume the variables, next thing is that you have to mathematically formulate the profit function that is to be maximized. You have to formulate the profit that has to be maximized. Now, it is mentioned in the problem that profit of 1 unit of product A is 600. Now, you are going to apply the unitary method which you learned in school. If profit for 1 unit of product A is 600, and you have assumed X units for product A, so the profit involved will be 600 into X. It is quite obvious. And similarly, since the profit for 1 unit of product B is 400, then, and as you have already assumed Y units for product B, then the total profit for product B with respect to product B will be 400 into Y. Now, 600X is the profit associated with the product A, and 400Y is the profit associated with product B. So the total profit, which I'm naming over here as capital Z, is 600X plus 400Y. Okay. So I have got two things from step 1 and step 2. From step 1, I have got the variables. From step 2, I have got a function, which is actually the profit function. And I'm going to maximize that. Step 3, I have to look for different constraints. Constraints are actually known as restrictions, different sort of restrictions. Now, these restrictions, which you have to identify the problem itself. Okay, in mathematics, these restrictions are also known as constraints. So what sort of different constraints are present in the problem? We have to identify it. So if we go through the problem, we will find various restrictions. So I have named those restrictions carefully. Restriction number 1, if you can see the question, you'll be able to see it later, that maximum number of units of capital A that can be sold is 7,000, and maximum number of units of capital B that can be sold is 10,000. Now, when we say that the maximum number of things you can sell, I'm actually putting some sort of upper bound. You cannot cross it. Okay, you cannot sell your product. Number of selling shouldn't exceed 7,000 for product A. Number of units shouldn't exceed 10,000 for product B. So I'm putting some sort of upper bound. And therefore, when it is done, actually immediately after that, you are getting no equality, you are going to get inequality. So that's why with respect to product A, I have written this restriction in the form X is less than or equal to 7,000. 7,000 is the upper bound, and Y is less than or equal to 10,000. 10,000 is the upper bound. This I call as restriction number 1. Then your job is to look into the problem once again and look for any other different sort of restrictions are present or not. If not, then you have to stop over here. If yes, then you have to note down that also. Since I have already done the problem, so you have already seen that I have mentioned restriction number 1. So it immediately implies that naturally some sort of restriction number 2 is also present. So let's see what is that. Restriction number 1, which I've mentioned in 1, is called as, I have named it as selling constraints. Okay, so this name which I have mentioned over here, I have put that name over here. What other constraints are present? Restriction number 2 is the production process has a total capacity of 45,000 man hours, and it takes 5 hours to produce a unit of capital A and 3 hours to produce a unit of capital B. So some sort of time constraints are present. So here I'm writing it in this following way. 1 unit of capital A requires 5 man hours, and so X unit of capital A requires 5X man hours. 1 unit of capital B requires 3 man hours, and so Y units of capital B require 3Y man hours. Therefore, we must have 5X plus 3Y less than or equal to 45,000, because it is mentioned the production process has a total capacity 45,000 man hours. It means here 45,000 is also a sort of upper bound. Okay, the production process cannot exceed that man hour. Therefore, less than type of inequality has been taken into consideration. Here you can consider this constraint as man hour constraints or time constraints, whatever you call them. These restrictions, restriction number 1 and restriction number 2, are actually known as constraints. Apart from this, there is a different constraint. Okay, somebody has written something in the chat box. Oh, roll number, sorry. Now, apart from these restrictions 1 and 2, another type of restriction is present. This restriction is called non-negativity restriction or non-negativity constraints. What are they? You will see that in the question, it has been asked how many units of A to be considered and how many units of B to be considered to maximize the profit. How many is a real variable. This is physical variable. When we talk about how many, this how many cannot be negative. How many students are at present in my class? So I cannot say that there are minus 31 students are present in my class. It's a bogus sort of thing. So you know that when you deal with a physical variable, this sort of physical variable, which counts something, that physical variable is always non-negative. Either it is 0, no units are present, or it is something positive. So therefore, a non-negativity restriction has to be put in the problem formulation, and you have to write that X is greater than or equal to 0 and Y is greater than or equal to 0. Okay. Now, after that, you have to summarize the entire thing which you have done in above together. You have to write them together in a special way. And so I have written it over here. So I have combined these different items which I have considered above. I named those as 1, 2, 3, and 4. So combining 1, 2, 3, and 4, I have written that let us maximize capital Z. So I have written maximize Z. Okay, where you know already that capital Z is the variable which defines total profit. So maximize capital Z. The profit function was 600X plus 400Y. Okay, and this profit maximization is subjected to the constraint. What are the constraints you have got? The constraint for man hour constraint which you have got is 5X plus 3Y less than or equal to 45,000. And another constraints we have got that X has to be less than or equal to 7,000 and should be greater than or equal to 0. So combining these two, I have written it over here like this. And from the second one, I have written 0 less than or equal to Y less than or equal to 10,000. Now all the parts present in this equation number, in this, I shouldn't say equation, in this part, this particular portion of the problem has been marked as star. So in star, various types of items are present. So this star entirely constitute the linear programming problem. Why it is linear programming problem? Because you see that in the profit function, the variables X and Y has power 1. In the constraints, the variables X and Y has power 1. Okay, if you consider at least one variable's power to be more than 1, say for if I could have got 5x square plus 3y everything else has power 1, then it is not linear programming problem. Each and every variable present everywhere in every part of the linear programming problem must have power 1. Now, this different parts of star have different names. So let me tell you what the names are. Okay. First of all, we considered the variable x and y. Those variables, the quantities of those variables actually decide whether your profit will be maximized or not, how will it be maximized. So these variables x and y, they are called decision variables. Okay. Those variables x and y, they are called decision variables. If anybody wants to say anything, he or she can write in the chat box. Okay. Now, the variable x and y are called decision variables. When we write that these variables are non-negative, we consider the non-negativity constraints. And other than non-negativity constraints, we have different type of constraints: selling constraints, time constraints, man-hour constraints, credit cost constraints, whatever, seat capacity, whatever, it depends upon the situation. And lastly, this function, which you are supposed to maximize, that maximize z equal to 600x plus 400y, that function is called objective function. This function is called objective function. Okay. Now, here I have mentioned these various parts of the linear programming problem. Linear programming problem actually consists of 4 different parts: variables, a function to be maximized, restrictions, non-negativity constraints. And I have also mentioned over here what are these different parts known as. Okay. So if any of this part, if at least one of these parts are missing, then your linear programming problem is not complete. Your linear programming problem will be complete if all the parts are present over here. Second thing which I would like to mention over here is that you can consider this linear programming. Once you see that, yeah, these are the different parts of the linear programming problem, can I generalize this? Can I write the formulation of linear programming problem in a general sense or not? So instead of considering 2 variables, you can consider n variables. So which I have considered over here: x1, x2, xn. These are the n variables in general of some linear programming model. And suppose, since in this present, in the above question, we considered how many constraints we actually considered? We considered 3 constraints. Man-hour constraint, only 1 man-hour constraint was present, and 2 selling constraints were present. So in general, I'm considering small m number of constraints. Say, now this small n and small m, how many variables are present in the above problem? 2. And how many constraints are present in the above problem? 3. Okay, so it tells us that the number of variables shouldn't always be equal to the number of constraints. So sometimes number of variable is more than number of constraints. Sometimes it is equal, sometimes it is less. Okay, so this n and m, n is the number of decision variables and m is the number of constraints. This n and m, they are not equal. Objective function, what did you get? You get, as I can recall, 600x plus 400y. Now 600, we actually call it as net contribution of the variable x. In linear programming problem, we call it as net contribution of the variable x. So, and this 400 is the net contribution of the variable y. Per unit, or sometimes it is called per unit contribution of the variable x is 600 and per unit contribution of the variable y is 400. Okay, so in the general case, we have considered per unit contribution of the variable x1 is c1, per unit contribution of the variable x2 is c2, per unit contribution of the variable xn is cn, and all these per unit contributions have been added together. And since it is a general case I'm writing over here, so I have not used the word maximize or minimize. I have used the word optimize, because optimize is the general word for both maximizing and minimizing. What was the next part which I considered in the previous case? I wrote this word subject to. Often people forget to mention this word. You shouldn't. This objective function will be maximized or minimized subject to the following constraints. So this word is very important. So in the general case also, I have mentioned subject to, and the variables if you consider the inequations here, you see that the coefficient of the variable x was 5 and coefficient of the variable y was 3. And on the right hand side of the inequation, some number was present. Here, the coefficient of variable x is 1. Y was not present. Here, the coefficient of variable y is 1. X was not present. So if I keep this in mind, in the general case, I can consider those constraints as a11 x1, a12 x2, and so on, a1 and xn. And in this manner, if you go on, you will get am and xn. So number of n variables and m inequations or equations or mixture will be present. In the bracket, I have mentioned less than or equal to, greater than or equal to, or equal to. Their mixtures can also be present. You can get a type of linear programming problem where one constraint is inequality, is having less than type of inequality. Another constraint is having greater than type of inequality. Another constraint is having equality. So a mixture can also be present. So since I'm writing the general form, I have considered all the possible symbols over here, either this or this or that. And in the right hand side, I'm considering the numbers b1, b2, bm like this. What was the most important part of the above problem? That these variables x1, x2, xn, these are actually non-negative variables. So that's why I have mentioned x1, x2, dot, 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 xn greater than or equal to 0. And obviously, already I've mentioned that m is not equal to n, and therefore, this is the model. Often it is asked in the examination. This model is called the general form of the linear programming problem, linear model. Okay, so here I've mentioned the per unit contribution of the variable xi's are ci's, and bi's are actually called the requirement vectors. Now, you can see that previously we have dealt with system where only equations were present. And now you are dealing with a system where not equations, but inequations are present. So linear programming problem, you can get a mixture of equations in inequations as well. And this, I'm not telling you how to solve this, but I'm only talking about the formulation part. So this is the general form. And if you ask me that, can we consider only the equality, or can we transform those inequalities into equalities? Or if we transform those inequalities into equalities, what will happen? Everything will remain same. Everything will remain same. Some methodologies are there by which that can be done. And if we consider only, if you can get a system where only equalities are present, this sort of linear programming model is called standard form of linear programming problem. But if you are given a generalized form of linear programming model, and if you are asked to write standard form, if I ask you to write the standard form of this model, which is in front of you right now, I cannot just erase the inequalities and put equality sign over here. I cannot do it forcefully. Some mathematics is there by which that can be done. So do not think that this standard problem, which I have written here in green color, is the standard form of the above generalized problem. consider these two parts separately, okay? Because here I have not told you, I have not shown how to get standard form from the generalized form. When I'll be doing the simplex method, that particular part will be discussed, okay? But if you are asked to write the standard form in the examination, you have to consider this system one, and if you are asked to write the generalized form, you have to write the entire system, this which I mentioned as G1. Okay, so here I'm only talking about what is the distinction between the generalized form and the standard form. And not only this, the above system can also be written in the matrix form also. So you can consider, say, I have mentioned over here that in here you see that I have written optimize capital Z equal to Cx, where I have written C is the row vector, C1, C2, Cn, and capital X is the column vector. So I have put a transpose over here. I'm putting transpose means it is in the form of column. I have mentioned it over here, as you can see. So if you multiply this row by this column, number of columns present here is n and number of rows present here is n. If you multiply them, you will get that objective function, which is this obviously this variable capital X is greater than or equal to 0. Here 0, 0 is 0, 0 is the column vector. This column vector will be treated as the 0 vector, and entire thing can be written in the matrix form in the following way. So this is the matrix form of the linear programming model. I have less than 1 minute, so I am stopping at this particular point. In the next session, I'm going to carry forward with further discussion on our today's topic. So I'm stopping here right now.